Okay, next step is to prove the correctness of this conversion algorithm from NFA to DFA. And the proof is unfortunately not very enjoyable, but that's how it is. So we're given an NFA N, and we saw an algorithm to convert it into a DFA D. And the claim is that the languages are equal. And we are going to prove a stronger claim that shows that for every string, the transition function, when we convert it into strings, on the NFA from S on W is equal exactly to the configuration that the DFA is going to be after we apply W, starting from the start state of the DFA, which is S prime. Okay, so this definitely implies the theorem, right? Because if indeed the DFA is a faithful simulator, which is that what the lemma says, right? For any input string, the current state of the DFA encodes perfectly the current configuration of the NFA when given this input, then we will get the same language because the DFA accepts in a certain configuration if and only if the NFA accepts in this configuration. So this lemma indeed implies the theorem. Right. So we need to prove this lemma, and we prove this lemma by induction, right? For many of the proof we will see in this course that we will use induction. This in some sense should be your default technique to proving thing. It's not the only technique, but it's probably the most popular that we're going to use. Okay, so since we're going to do induction, we're going to do induction on the length of the string W. So we're going to start with the empty string as our base case. And of course, there, the transition function of the NFA on the empty string is just going to be the epsilon reach of S. Similarly, for the DFA, feeding the DFA epsilon keeps it in the current state, which is S prime, but S prime by definition was the epsilon reach of S. So they are both equal, right? So that proves the base of the induction. Okay, so the inductive step is a bit more tedious, so let's do it. So the idea is that we are now going to look on a string, W, which is XA. X is a character. Okay, so this is the suffix definition of a string. And now we are going to do the following. We look on the transition of the NFA on its definition. And the definition says that this is, we first look on all the states that we can reach with X from S, right? And from there, then we apply, this, for each one of those states, we apply the transition on the character A, and we take the union, right? Okay. Now we just need to use the induction, right? So let's see. For the automata, for the DFA-D, when we apply XA, right, we first have to do the transition on X, and then the transition of whatever state we get on A. This is the definition of the transition function for D. And now we apply the induction, right? So what does the induction say? The induction says, well, when you apply the transition function on Sx, it's going to be equal to delta star of D on Sx, right? This should be S prime here, by the way. This is a typo. And the reason, of course, being that X is a shorter string than W, and as I we can apply the induction hypothesis, which we did not state, but that's what it is. Okay, so now let's go back to our definition. So this is the configuration that the NFA is going to be in, we now replace the union to be over the states in Y by definition. And this, of course, right, this is the definition of delta D of YA, right? This is exactly what the definition of the transition function. And as such, we can now put things together, right? Therefore, the transition function of n on Sx8 is equal to delta D of y, which is equal to the transition of D on this, which is equal to this. This is, sorry, another typo. This should be D. And this is what we needed to prove, so QED. Right? Okay. So this is one of those inductive proofs which are not very insightful, right? All they essentially say is that in every step, the DFA faithfully simulates the NFA, and as such, the result is correct, right? You just need to apply it inductively to get the overall result. Okay.